All right, we have another day of AP Psychology, another review day. We're going through all 7 of the units, and today we're going over the second unit. Last time we went over the first one, which was Scientific Foundations. That's the history of psychology and research methods. Today we do all of bio. And then 3, 4, 5, 6, and 7 are sensation and perception, learning, cognitive, developmental, and motivation, emotion, and personality. We are not doing clinical, although we already did that, but it will not be on the AP test. And we're not doing social. And that'll leave us a couple days to review and practice up on our FRQ, because as you know, that's the only thing that will be on this year's AP test. Here's what we're going to be going over today, which includes all of the biological psychology unit you can see here on my notepad. The anatomy of a neuron, the action potentials, neurotransmitters, brain anatomy, and sleep. Brain waves and all that, and sleep disorders. It's an enormous amount of information to cover. We're going to go very quickly through it. So this would not be, of course, all of you have already had the class, so it's not going to be learning it, it's going to be reviewing it. It'll be at a speed appropriate for reviewing, not learning. Additionally, it's not going to be exhaustive. So if you're looking through Quizlet, there's going to be lots of terms I'm not going to go over. We're going to go over the overarching ideas, not necessarily every single term. Especially since this is an FRQ only year and no multiple choice, I think that's much more appropriate. So, also, if we went over everything, this video would be extremely long, and I don't want it to be extremely long. So, we're going to go real quick. Starting with the anatomy of a neuron. So, you've all seen me draw this on the board lots of times over the years. I'm not going to draw it because I already have pictures of it. So, here's a picture of it. Like any cell, let me back up. A neuron is a brain cell. Just a brain cell is called a neuron. There are 3 types of neurons. There are interneurons. Interneurons are the ones that are just in your brain, so that's neurons beginning and ending in your brain. There are motor neurons, which are neurons that allow you to move your body. That's where the cell body, the brain of the cell, would be in your brain. And then there'd be a long axon that would go to your muscles and allow you to move stuff. Then there's sensory neurons, which would be this one, and that begins in your muscles, or I guess not really muscles, it would be in your, well, it would allow you to feel. So it would begin in your hand and move up to your brain when you sense things, sensory neurons. And so this is one neuron. It's either going to be very short or very long, depending on if it's an interneuron or which would be short, or a motor or sensory neuron, which would go all the way through your spine, be very long, several feet long. 1, like any cell, is going to be the nucleus of a cell. 2, also like any cell, is going to be the cell body or soma of a cell. 5 is the arms that extend out of the cell. They are the ears of the cell. They listen for other messages from other cells. 5 is the dendrites. On the other end of the cell, kind of the opposite of dendrites, is 8, which is the axon terminals. Axon terminals at the end, and it sends messages. So there's neurons communicate through electrochemical impulses, electrical impulses that are fueled by chemicals moving in and out. And 8 sends messages to other neurons. 5 receives messages from other neurons. 9 is the entire axon. That's the long expanse of the neuron that allows it to communicate with neurons that are not nearby. I'm going to skip 3 for a second. 6 is the myelin sheath. It is a fatty tissue that insulates the axon. It is broken in. There are multiple myelin sheaths that insulate the entire axon. And in between the myelin sheaths is 7, which is the node of Ranvier. Why there are multiple myelin sheaths and not one large insulation, I'm not sure, but that's what is the case. Number 4 is the Schwann cell. Schwann cell is a cell inside of the myelin sheath that creates the myelin. So it's the producer of myelin. What am I missing? I think that just leaves 3. 3 is the axon hillock. It's like the gatekeeper. When the voltage in the 1 and 2, so the nucleus and the cell body, rises enough to reach the threshold, then the axon hillock allows a message to be sent across the axon. It goes to the axon terminal and raises the voltage of the new receiving neuron, making that neuron more likely to send a message. And that's how, done this a bajillion times, is how we think and feel and have emotions and all that. So that's the anatomy of a neuron done in just a couple minutes. Great. Action potentials. An action potential is just the electrical process of a signal being sent across the axon. And it is measured in millivolts. So up here is positive 40 millivolts, up down here is negative 90 millivolts. And usually the process of an action potential goes from positive 40 to negative 90 in a very predictable sequence. So the resting potential is negative 70 millivolts, meaning that in a neuron, if nothing's happening, it is negatively charged by roughly exactly negative 70 millivolts. So right here would be negative 70 millivolts unless he has been sent a signal from one of the attached neurons, in which case, usually, it will increase the voltage. So right now he's hanging out at negative 70. If he receives a message through his dendrite, then it will raise his voltage. If it ever reaches up to negative 55, which is this point right here, I'll just draw a solid line right here. So if it ever reaches this line, then it will reach the threshold and an action potential will occur. So once the action potential occurs, it goes through this predictable sequence. And this is regulated by the axon hillock number 3. It goes up to positive 40 millivolts, down to negative 90 millivolts, and then back to the resting potential, which is negative 70 millivolts. This is also partially regulated by what's called the all or none principle, meaning that you can't have an action potential that only goes to positive 30 millivolts. It always goes up to exactly positive 40, never more, never less, and always goes to exactly negative 90, never more, never less. The process of it raising in voltage is called depolarization. The process of it going back down is called repolarization. And the process, once it is below the resting potential, that's called hyperpolarization. And then this whole time period before it gets back to the resting potential is called the refractory period, which is, it has to completely recharge back to negative 70 before it can send a new message across. And that is the electrical process. All of this is governed by a chemical process. There's sodium and potassium inside and outside the neuron. Usually sodium is outside, potassium is inside. There's a thing called voltage-gated channels. Most of you should remember at least part of this. And once we hit the threshold, the voltage-gated channel for sodium opens, so sodium rushes in, which is actually what causes the voltage to go up, because both sodium and potassium are positively charged. So once sodium goes into the neuron, or the axon actually, there's a whole bunch of positively charged stuff on the inside, and that raises the voltage. Once it gets up to positive 40, the sodium gate closes and potassium gate opens, making the potassium go outside, and that decreases the voltage because there's a bunch of positively charged potassium that leaves until it gets to negative 90, and then both of the gates close, except that now potassium is on the outside and sodium's on the inside, and there's a thing called the sodium-potassium pump, which slowly gets sodium and potassium back to where they were in the first place, which gets the charges back to where they were in the first place. And that is the action potential process, both electrically and chemically. Now let's talk about how neurons talk to each other. They talk to each other. Two neurons will actually not quite touch each other, but they'll get really close to touching each other through the axon terminal and the dendrite. So if there's two neurons that are communicating, their axon terminals and dendrites are very close to each other. You can see in this picture, this 8 here is the axon terminals, and this 5 here is the dendrites, and this area right here is very close to touching. That would look like this if we magnified it with my very bad Microsoft Paint artistry. This then would be the axon terminal. Let's make that a little bit bigger. And that would make this the dendrite. In between the two, they don't actually touch, there's a small gap. That gap is called the synapse, or the synaptic cleft, but we'll call it a synapse. in the axon terminal. Whenever an action potential goes across, it actually releases little chemicals called neurotransmitters. For some reason in my mind, they're always green. We'll give them 5, 4, and 5. 5 neurotransmitters. They're called neurotransmitters, or neuron transmitters. That makes sense. Oh, come on. Neurotrans. That a little bit smaller. They're called neurotransmitters, chemicals that are inside of the axon terminal. Once an action potential successfully comes across the axon, it releases the neurotransmitters into the synapse. So, action potential comes across, boom, they go into the synapse. Then they bind to what's called a receptor site on the dendrite. So here's little receptor sites. Once an active potential comes across, they release the neurotransmitters into the synapse, and they go into, well, they release them from the axon terminal into the synapse. So then they go into the synapse once an active potential successfully came across the axon, and they go into receptor sites. If there are, this is important, if there are receptor sites that fit. In this case, I drew a whole bunch of circles, and these receptor sites look like half circles. Perfect, they fit. Great. If they fit, then they bind to the receptor site, and they send a message to the receiving neuron, which increases or decreases depending on what kind of a neurotransmitter it is, but usually increases the electrical signal of the receiving neuron. Then, after they are done binding, they will go back into the axon terminal in a process called reuptake. So here they go back. That is called reuptake. That is the process of neurotransmitter transmission. Now, this process is different depending on which neurotransmitter we're talking about, which will be the next thing we talk about. So let's talk about the types of neurotransmitters we have. The ones we care about the most are serotonin, dopamine, acetylcholine, and GABA. And they do different things. These 4 are different kinds of neurotransmitters. So these neurotransmitters are a certain type of neurotransmitter, and they could be one of these 4 things or lots of others, but these are some of the main ones that we want you to know about. Serotonin, and here's, it gets very complicated, but a very oversimplified approach is this is how they function. We'll go function, too much, and too little. General function, what happens if it's too much, and what happens if it's too little. Serotonin, the general function is mood, although all this is kind of oversimplified. If you have too much, I'm actually not even going to put that there because that would just be too confusing. But if you have too little, you would have depression and anxiety. Depression and anxiety. Dopamine is also kind of mood. I'll put an asterisk because it's mood and a whole bunch of other stuff. But if you have too much dopamine, it can cause schizophrenia, or at least schizophrenia is overactive dopamine receptors. So too much dopamine would cause schizophrenia or psychotic symptoms. Too little dopamine would cause Parkinson's disease, which doesn't seem to make any sense because schizophrenia and Parkinson's seem to have nothing to do with each other, but that's what it does. The function of acetylcholine is movement. This font is too big. So acetylcholine is movement, and so then having too much, either too many acetylcholine neurotransmitters or too much acetylcholine receptor sites or too much communication using acetylcholine would cause seizures, which is basically moving too much, and then too little would cause paralysis. These 3 neurotransmitters are called excitatory, meaning that if any of these 3, serotonin, dopamine, and acetylcholine, as well as most of the others, successfully bind, they raise the voltage of the receiving neuron, meaning it'll raise it from -70 to a higher voltage, getting it closer to the threshold. GABA is an exception to this, and it is actually an inhibitory neurotransmitter. It will decrease the voltage of the receiving neuron, making it less likely to send a message. It's not really the function, but one important thing to know about GABA is that it's what alcohol uses. So not really function, but that's okay. Which is why they say alcohol is a depressant, because it literally depresses your neural communication. So that is that. There are basically only three ways that drugs, whether natural, legal, illegal, recreational, whatever, can work. And they are as agonist, antagonist, or a reuptake inhibitor. That's the only three ways that drugs can work. And by drugs, I mean cocaine, but I also mean Advil, alcohol, getting bit by a black widow spider. All those count as, they all interfere with your neural communication process. Agonist mimics the way a neurotransmitter works, and it fits into the receptor site and fires enough to send a message. So if you took, let's make this blue. If you took let's say, acetylcholine. So acetylcholine, if you took an agonist of acetylcholine, it would be you would introduce into your bloodstream, into your synapses, a molecule that is not acetylcholine, but it looks enough like acetylcholine to act like acetylcholine. Whoa. So it would be this, you took a pill, and it looks like acetylcholine enough to fit into your synapses, and since it's the same shape, it fits into the receptor sites and sends a message. So agonist fits into the receptor site and sends a message successfully. An antagonist would be like a pill or any kind of substance that would go into your body that looks kind of similar to a neurotransmitter, but not enough that it actually fits in the receptor site. So it still goes into your synapses, it fits in the receptor site, but it does not send a message. So it clogs the receptor site and does not send a message, which then makes it impossible for your actual neurotransmitters to fit into the receptor site and send their own messages. And effectively, this does the opposite of what the neurotransmitter would have done. Two examples of this are with acetylcholine. There is poison dart frog. The juices from a poison dart frog works as an antagonist of acetylcholine. So here's a poison dart frog. You lick it or get shot by a poison dart with poison dart frog venom. It introduces antagonist of acetylcholine into your system. It floods your receptor sites with these things that look like acetylcholine but clog up your receptor sites, making your acetylcholine not able to work. And your acetylcholine is used for movement, so now you can't move, and then you're paralyzed, or if it's enough of it, then your heart's paralyzed, and that means you die. Black widow venom works the opposite. It works as an agonist of acetylcholine, and that would be, it floods your body with molecules that look like and act like acetylcholine. So instead of your normal amount of acetylcholine, which lets you move normally, you have too much acetylcholine, which floods your synapses with essentially more acetylcholine, making you move more, which is seizures. That's why if you get bit with enough venom from a black widow, it'll make you start having seizures. Reuptake inhibitor is the other way that drugs can work. Common antidepressants, so Lexapro, Zoloft, those kind of things are all reuptake inhibitors of serotonin. So serotonin, the way serotonin works is if you have enough of it, you are normal and you don't have depression. If you don't have enough of it, you'll have depression, or at least you'll be more prone to it. There are a couple ways to fix this. One will be with taking an agonist of serotonin to introduce more serotonin into your synapses. There's a few problems with this, like it tends to be it's faster acting, which also means it goes away faster. You could also take a reuptake inhibitor, and that keeps your existing supply of serotonin, which is lower than normal people, which is why you have depression. But once your serotonin go into the synapses and bind, instead of going back in the process of reuptake, it prevents the process of reuptake. So your serotonin goes into the synapse, it binds, and then ordinarily it would go back, but it can't. So it stays in the synapses and it binds more easily next time. So next time an action potential comes across the synapse, the axon, and releases these things, they don't even have to go from the axon terminal to the synapse because they're already there. So they have less distance to travel, which makes it easier for them to send signals. So you have less of them, but they work more efficiently. Now we'll talk about the nervous system and then the brain anatomy very quickly. The nervous system is broken down into two categories of the nervous system, the central and peripheral nervous system. This is not very good at showing the difference, but the central nervous system in this blue here is just the brain and spinal cord. So the brain and spinal cord show up in blue in this picture, and that's it. The peripheral nervous system does not include the brain and spinal cord, it's just all the other stuff. So all the peripheral stuff. So basically, central nervous system is made up of interneurons, and then peripheral is the motor and sensory neurons. Divided into that. The peripheral nervous system further subdivides into autonomic and somatic. As you can see here, autonomic is all of the things that are automatically, easy to remember, autonomic, automatic, controlled, and somatic is voluntary control. So when I'm moving my hands like this, that's controlled by the somatic area of the nervous system. Autonomic would be like heartbeat, things that happen automatically. Of the autonomic, it further subdivides into sympathetic and parasympathetic nervous system. The parasympathetic nervous system is the calming side, and the sympathetic nervous system is the arousing side. So heartbeat increases, that would be sympathetic. Heartbeat slows down, would be parasympathetic. Brain anatomy. So the brain is divided into two hemispheres, which is the right and left hemisphere. So if you were to divide your brain in half, of roughly equal mass, but they do a little bit different things. Although to say that one has to do with intelligence and one has to do with creativity is definitely oversimplifying. But in the middle and connecting the two hemispheres is the corpus callosum, which is this little band of tissue right here. It is divided into 4 lobes, which cross both hemispheres. The frontal lobe is in front, parietal top, temporal bottom, and occipital back. Frontal lobe, complex decision making generally. Occipital lobe has to do with vision generally. The limbic system is like the system of organs inside of your brain, and I'll talk about some of the most common ones. There's the corpus callosum again, connecting the two hemispheres. The brain itself is divided, can I make this bigger? Is divided into, perfect. The big part of the brain, which would be the cerebrum. So all this stuff right here, what you think of as the brain is the cerebrum. The part on the bottom, so this part here on the left side and this part here on the right side is the cerebral cortex. Sorry, not the cerebral cortex, the cerebellum. The cerebellum is the little brain on the back bottom of the brain, and the cerebrum is the big brain. The cerebral cortex is the outer part of the cerebrum. Here, so all these pink folds are the cerebral cortex. The brainstem, which is at the top of the spinal cord, leading into the brain, is made up of the pons, which is the swelled part of the brainstem, and then the medulla. The medulla regulates heartbeat and breathing. The reticular formation is inside of the brainstem, and reticular literally meaning net-like formation. It is a bundle of all of the neurons that are the nerves, which are bundles of axons going up, leading into the brain. So the reticular formation is made up of all of that is traveling through the brainstem on its way to the brain. Speaking of that, there's the thalamus, which is right here at the top of the brain, and that is where all of the axons from the neurons are routed to go where they're supposed to go in the brain. So they then connect to their appropriate areas in the brain in the thalamus. So thalamus is the routing area. It says relays messages between brain areas here. Then the actual parts of the organs inside of the brain would be made up of things like the hypothalamus, the amygdala, and the hippocampus, at least listed here. Hypothalamus is the reward center of the brain. So it things like eating, reward, addiction is highly governed by the hypothalamus. That is governed there. The amygdala has to do with emotion, aggression, and fear. If they stimulate the amygdala of a cat, it'll make the cat hiss and get angry. If they lesion, which means destroy, parts of the amygdala in a cat, it then can't get angry or scared. Hippocampus has to do with memory. So that's this big blue swirly seahorse looking thing is the hippocampus. So now let's talk about sleep. There are 5 stages of sleep. They are not very creatively named. They are named stage 1, 2, 3, 4, and REM. 1, 2, 3, and 4 make a lot of sense. REM stands for rapid eye movement. This is measured in an EEG, which is that skull cap they put on to measure electrical activity in your brain. It doesn't actually give you a picture of your brain, just measures the amount of activity, brain waves. So this is what alpha waves are, awake waves. All the other ones, 1, 2, 3, 4, and REM, which they call stage 5, is sleeping brain waves. Stage 2 has what's called sleep spindles. That's what this little burst is right here. Let me move this over. So 2 has sleep spindles, that's that. 4 has what's called delta waves. Delta waves are these, you can see them here, these slower lethargic waves. Actually, stage 4 is going to be your deepest physiological sleep. Your body temperature will actually be the lowest, and you'll be hardest to wake up in stage 4 sleep. REM, rapid eye movement sleep, it's the only one where you dream. So it's the one where you are dreaming, and it's rapid eye movement REM sleep because your eyes are literally jolting back and forth very rapidly. Circadian rhythm is your body's natural sleep-wake cycle, so that's you go through, that's your cycles of every 24 hours, every day, you go through sleeping and waking, and then roughly every 90 minutes, you'll go through all of these stages. So you'll go through 1, 2, 3, 4 REM and back. It doesn't always go, in fact, you kind of get shallower and shallower, more quickly to REM as the sleep progresses. Additionally, if you are sleep deprived, you will go quicker to REM, or if you're very sleep deprived, you might even skip all the stages and go straight to REM. So if you sleep for 6 hours, you would then go through 4 sleep cycles. So normal 8 hours sleep would be roughly 5 times all the way through, which is why you'd have multiple dreams in a single night. 2 types of hallucinations. Hypnagogic hallucinations are hallucinations that occur as you are falling asleep. So as you're awake at 10 p.m. whatever, and you're entering stage 1 sleep, you can have hallucinations. And then hypnopompic is as you're waking up. So that's the middle of the night you wake up and you can actually visually hallucinate into the room. There are a little bit of differences. Primarily, hypnagogic tend to be more vague. You can feel like you're pushed into your bed, a sense of impending doom, and a dark shadowy figure is above you. Is the most common things. Hypnopompic hallucinations can be much more vivid, so you can actually see things. Like I've heard of people that see spiders, bears, wolves, people, much more real feeling, I guess. Let's see. NREM is the name of every stage that is not REM. Again, very creative. Sleep disorders. Insomnia is the inability to go to sleep. Narcolepsy is falling asleep while you're awake, which ironically can be triggered by excitement, so you scare someone and they fall asleep. So that pretty much wraps up this unit. Again, we went incredibly fast, and I skipped some stuff. I was just trying to get the overarching themes. And definitely was for review and not for learning it the first time. But I think this should be a pretty good refresher. Hopefully a lot of that sounded familiar. But all you have to do today is just listen to this lecture and then do the Google form stuff. But I'll see you next time when we talk about sensation and perception, which should be pretty fun.